Welcome to yet another of my messy videos. If you are planning to develop a strategy game, you will most likely want to create a hexagonal grid, because regular hexagons are prettier than squares, and for many other brainy reasons. On the other hand, hexagonal tiling is more costly than rectangular, because it requires more calculations, tiles, triangles. But we don't care about that, so today is the day of the hexagon. In this video tutorial, we will see how to create a large planar map composed of hexagonal tiles, in which to place static 3D objects and make the characters move. Since we can divide the map into smaller adjoining areas of equal size, we are only interested in creating one area. To place and find the hexagons on the map, we need to use different coordinates. The usual ones of the 3D world, which I call world coordinates. Since Godot uses X and Z axes as defaults for the horizontal plane, we will use them for the grid. Then axial coordinates, which are used to target cells on the two-dimensional map. These should be better linked to the pixel coordinates of an image. And maybe cube coordinates, which are supposed to make everything easier. We will analyze only one particular case useful for a demonstration. Furthermore, it would be great if I could get map data right from an image, because it can be easily modified using an image editor. Ultimately, I would like all of this to be smooth and fast. The video is split into two parts, theory and practice. Now let's start with the theory. I recommend you not to skip this part, but if you are not interested or can't stand math, you can jump over the hurdle and go directly to the second part. At 7:24, we got our flat pointy top hexagonal tile laying on the XZ plane in world coordinates. Since we are working in a real 3D space, not bound to pixel perfection rules, our hexagon is regular, thus it has all sides and angles equal. Let R be the radius of the circle within which the hexagon is inscribed. The height of the hexagon is on the W sub Z axis and is simply equal to twice R, thus the diameter of the circle. Instead, the width is on the W sub X axis and is equal to twice of this segment. The length of this segment is the cosine of 30 degrees multiplied by R, which is equal to square root of 3 over 2 multiplied by R. So, the tile width is square root of 3 multiplied by R, which is also the distance between the centers of two nearby hexagons on the grid. If we want the horizontal distance between two tiles to be unity, we can set R equal to the inverse of the square root of 3, and measurements will change accordingly as shown. Now we need to set up axial coordinates, and I choose these indicated in light blue because they resemble classic 2D screen coordinates. Looking at the coordinates, we can find the two directions where they stay constant, thus the axial axes are orthogonal to these directions. The red axis for the X coordinate on the right and the green axis for the Y in the center. It's time to calculate the world coordinates from the axial ones. Since W sub Z does not change by varying A sub X, it depends only on A sub Y, so we can easily find their relation. Whereas W sub X is given by the sum of the contributions of square root of 3 times R when A sub X is 1 and A sub Y is 0, and minus square root of 3 over 2 times R once we increment A sub Y by 1 unit. With some substitutions, we can also find inverse relations, as shown below, and convert them all into a matrix form. By using integer axial coordinates as the pixel coordinates of an image, we can paint the hexagons of our hex grid with the image colors. That's right. And we can also round the result of inverse formulas to find the axial coordinates from world coordinates. It's too simple, isn't it? Yes. Indeed, it doesn't actually work that way. It would not work for every point in the plane, because by simply rounding the coordinates would not find hexagons, but trapezoids. To understand this point, we better at the third axis and move to cube coordinates. In this specific case, cube coordinates are an extension of axial ones, with an additional constraint. Y-coordinate must always be the sum of the other two. If we mark with dashed lines the points where rounding applies, we can reveal a triangular region among the hexagons. The Devil's Triangle. Here be dragons. Let's try. Moving around the triangle, we notice the problem caused by independent rounding of cube coordinates. Each coordinate goes on its own, without taking into account the constraint in any way. The solution is majority wins. That is, the closest axes after rounding control the constraint, hence the displacement. Let's try again. I'm using metal springs now in order to show distances, but it works contrary to how it seems. The spring that pulls the hardest is the one that gets ignored. No way around it. So, since this works, we can write the cube coordinates formulas which, in addition to the expensive plane coordinates, also include a fourth coordinate, representing the y-axis in Godot world coordinates, always in matrix form. Why matrices? Because they are prettier, of course. And also because, for some reasons, matrix and vector operations in GDScript are much faster, especially if we reuse object instances. Now that we know the theory, we're ready for the second part. Let's move quickly. Here is the base project, made up of a simple world environment node, a directional light, the usual camera 3D node with a basic animation script attached, and a shabby fiddling mysterious node. The main node has an attached script that is used to load the map from a PNG image and make it available to the underlying nodes as a global variable. The image is actually a sample height map that we'll use shortly. The basic map class holds the entire map as one large image and provides the color values at the different pixel coordinates, or rather integer axial coordinates. The code is quite nutty because I'm trying to make it faster using some tricks used in old games. I still don't know if it's worth it. Then we have the utility class for coordinate conversion. It contains some constants, the coordinate conversion matrices seen previously, and classes to represent the various types of coordinates. Actually, the fat cube coordinates are enough and convenient, but in some circumstances it is better to have leaner 32-bit only coordinates, like world and axial ones. This code looks a bit weird. It's because I'm experimenting with a way to reuse object instances to make it faster. Somewhere around here there is the method that rounds the coordinates. Looking at the resources folder, here is a sample mesh with the same dimensions as set in the XGD file, but before using it we have to enable the views as albedo a surface property. Let's create a multi-mesh instance and attach the basic script to it. From here on, we will build everything programmatically using GDScript. We instantiate the multi-mesh object as usual, enabling colors on a per tile basis. Then we build the grid area by setting up the right position and a random color to each tile. Here it is. It's boring, but we can change the parameters on the fly. So, let's animate the grid. the transform to change the height of the tiles to the corresponding value taken from the map. Here is the code we will use to change the parameters between the initial and target values once the animation starts. For simplicity, I'll trigger the animation manually using the Enter key. It didn't come out well. We need to better adjust the values read from the map. Now I use random values because there are other things to see. Multi-mesh is limited to a single mesh, but we can customize the transformation and color of each tile. And we can also apply a parametric shader to it, so we can do a lot with it. To test whether the cube coordinate rounding code works, I called Seer to show it, although it's always an unknown to let her do something on her own.